So to get started, we are first going to look at the first part of section 1 in chapter 2, and we are going to be looking specifically at power functions and how we can graph and analyze them. And a power function is a specific type of monomial. Let's begin by first looking at the definition of a monomial. So according to the formal definition, a monomial can be written in the form f of x equals a times x to the n, where a and n are any non-zero constant real numbers. Okay, so we're going to look at three different types of monomials today. We're going to look at their graphs and we're going to look at their various characteristics in order to analyze them. The first type of function that we're going to look at is just your generic monomial. So we might have a function f of x equals 3x cubed, or another type of function of this kind would be f of x equals 1/2 x squared. So anything like that where a and n are positive, they're not zero, that's the first type we're going to look at. The second type we're going to look at is when our exponents are negative. So here we might have 3x to the negative 3, or another type of function, 1/2 x to the negative 2. Okay, and we're going to look at those graphs and what they look like. And then the final function we're going to look at today is a function that has a rational exponent. So that is any sort of fraction that is in our exponent place. So we could have 3x to the 3/4, or another type of function we could have would be 1/2 x to the 1/2. Okay, so three different types. Monomials that have rational exponents, monomials that have negative exponents, and monomials that have positive exponents. So to get started, let's go ahead and look at the different things that we need to know in order to analyze and be able to analyze our function. So a lot of this is review, so I'm going to go through it pretty quickly. But the first thing that we need to do when we're analyzing a function is state the domain and range. So if you recall, domain is referring to our x values and range is referring to our y values. The third thing we need to look at is our intercepts. So we need to ask the question, where is our graph crossing the x and the y axis? The fourth thing we need to determine is the end behavior of the graph. So when we talk about end behavior, we are going to use limit notation. So we're asking ourselves, as x goes to infinity, what are our y values doing? And similarly, as x goes to negative infinity, what are our y values doing? Next, we are going to look at continuity, and we are going to determine the places where our function is discontinuous, if it is, and then if it's not, we're just going to write the interval on which it is continuous. And then finally, we're going to look at the intervals of where our function is increasing and decreasing. So that's just looking at our graph from left to right and determining those intervals. So let's go ahead and get started with an example. Our first example is f of x equals 3 times x to the 6th power. So this is just your generic power function, pretty basic monomial. And what we're going to do is we could create a table of values, but it's going to be a lot quicker if we just go right to our graphing calculator. And when we graph our function, we see that it looks something like this. So our graph is flatter on the bottom, but it has the general shape of a parabola, and that makes sense because our power here is positive. So the first thing we want to do is look at the domain. So the domain of a function, remember, are the x values. So our function, for all the x values, we see that all of them are going to give us outputs of y values. So our domain is going to be from negative infinity to positive infinity, or you can write it as all real numbers. Next, we want to look at the range and determine what the values of y are that make our function true. And we see that there's no negative y values here, so our function has a range from 0 included to infinity. Next, we want to look at the intercepts. Where does our graph cross our x and our y axis? And we see that the only place that it crosses, or in this case that it touches, is right at the origin. So we would say that our intercept is at x equals 0. All right, next we want to look at end behavior. So we're asking ourselves, as x is becoming more and more positive, what are our y values doing? So as we go along the x-axis into positive infinity, we see that our y values are increasing to positive infinity. Similarly, as we go from x to negative infinity, we see that our y values are also increasing into infinity. So we write that in the way that we learned last chapter, the limit as x approaches infinity, our y values are going to positive infinity. And then similarly, as x goes to negative infinity, we see that our y values are also going to positive infinity. So we just write it just like that. Next, we want to determine where our function is continuous. And as we are looking at our function, we see that we can draw this function without picking up our pencil. So because we can do that, we would say that our function is continuous everywhere. So all we have to write here is that it is continuous, and our interval is negative infinity to infinity, because everywhere our function is continuous. And then finally, we want to look at where our function is increasing and decreasing. And as we read from left to right, we see that our function is decreasing on this interval, and then at 0, it changes and it becomes increasing. So again, just as a refresher, we write decreasing, negative infinity to 0, not included, and then we're going to write 0 to infinity for our increasing interval of our function. Let's continue looking at and analyzing more functions, but this time let's look at a function that has a negative exponent. So let's say we have a function f of x equals 2 times x to the negative 4. Okay, so here is our negative exponent, and we can think of this as writing it in a different way. If you recall from algebra, the negative exponent means that the whole term is going to be in the denominator of a fraction. So we can rewrite 2x to the negative 4 as 2 divided by x to the 4th. Again, we could put all of our information into a chart and determine x values and y values by plugging in and determining coordinate points, but we have a graphing calculator, so let's use that. So we draw our axes here, and when we use our calculator, we see that our function looks something like this. So it's getting infinitely close to 0 on both axes. Okay, and again, when we analyze a function, we're looking at various aspects of it, and the first thing we want to do is identify the domain of a function. So the domain of the function are x values, and when we look at this function, we see that something a little wacky is happening with our x values. Here, we see it's continuous and it's including all these values, but as we get closer and closer to this 0, and if I had drawn my graph a little bit better and more accurately, you would see that the graph is starting to come up here. So it's getting closer and closer to 0, but it's actually never going to cross this line. So what we're going to have to do is we're going to have to write a union, because our function picks up over here as well. So we have to show that break in our domain. So the way we write that is we say that our x values of our domain are negative infinity to 0, and 0 is not included. And then we want to continue our domain by saying it's going to be united with the other half of our function from 0 to infinity. Now, looking at the range values, we see that our y values are only going to exist when they're positive. Again, it's not going to be equal to 0 because this side of the graph and this side are getting infinitely close to this 0 line right here, but they are never going to touch it. So we write this as the range from 0 to infinity. Okay, so we have the domain and the range, and now we want to talk about our intercepts. So does the graph cross our x or y axis anywhere? And looking at our graph, we would say that it never crosses, so we have no x or y intercepts. Next, we want to look at our end behavior. Now, this is going to be a little bit different, something we haven't really talked about yet in terms of chapter 1, but let's look at our graph here. As our x values are going to infinity here, right, we want to ask ourselves, what are our y values doing? And generally, in the examples we've seen, our y values have been going to positive or negative infinity, but they don't always have to do that. And in this case, you see exactly an example of it not going to positive or negative infinity, right? This side of the graph is not going to go up into infinity or positive infinity, but it's instead going to get closer and closer to 0. Okay, and that is happening on both sides. When my x's are positive, my y's are going to 0. And when my x's get more and more negative, my y's are also going to 0. So the way we write that is we say the limit as x approaches infinity of f of x, so this is still the same way we always write it, but instead of going to positive or negative infinity like we're used to, our graph is going to 0. And same thing when we approach the negative values of our function. So as x approaches negative infinity, our y values are also going to 0. The next thing we want to look at is continuity. And again, this is asking ourselves, can I draw my graph without picking up my pen? And it's obvious when we're looking at the graph that there is no way we can draw this continuously without picking up our pen. And so now we have to determine what type of discontinuity exists. And in chapter 1, we looked at the limits as it was approaching from the left and from the right at a certain value. But here we can look at and determine that there is going to be a discontinuity right here. Okay, and we will call this an asymptote. And in this case, our graph is going to be discontinuous at x equals 0. And why is it discontinuous? It's because there is a vertical asymptote at x equals 0. So the way we write that, we would just say that our graph is discontinuous at x equals 0. Okay, and that's all we have to write. The last thing we want to do is look at the increasing and decreasing intervals of our graph. So again, we're looking from left to right and we're asking ourselves, where is our graph increasing and where is it decreasing, and we want to write those as intervals. So looking at our graph, we can see that it is going to increase on this interval. So it's increasing, increasing, increasing. And then we have to pick up our pen, and as we continue reading, we see that this side of the graph is going to be decreasing. So the way we write that is we say that our graph is increasing on the interval from negative infinity to 0, because again, we're looking at our x values, and it is decreasing on the interval from 0 to infinity. So here it's increasing, negative infinity to 0, decreasing from 0 to infinity. We're always looking at x values when we're doing intervals, and remember, we're always using parentheses as well. The last kind of monomial function that we are going to look at in this video is monomial functions that have rational exponents. So let's look at the function f of x equals x to the 5/4. So again, we see that there is a rational expression, a rational number in the exponent place, and we can go straight to our graphing calculator and see that when we graph our function x to the 5/4, we get something that looks like this. Okay, so it's going up into infinity, it's a little bit flat, and it looks straight, but it's not quite a line. And again, we want to analyze it in all the different ways that we've talked about. So first thing we want to do is look at our domain. So our domain is our x values, and we see that there's no x values over here, and that it starts here at the origin and goes off into infinity. So we write our domain values as 0 included, because our function is included at the origin, to infinity. Now we want to look at our range values, and we see that in a similar way, our range values are not negative here, but they start at 0 and they continue up into infinity. So we actually write our range values in the same way that we write our domain values, 0 included to infinity. Now the next thing we want to do is look at our intercepts. So where is our graph crossing our x or our y axis? And we see that the only place it is crossing the axis is actually at the origin. So we would say that we have an intercept at x equals 0. Next, we want to determine the end behavior of our function. So again, we are looking at what is happening when our x values are positive and what is happening when they're negative. Well, in this case, our x values, nothing is happening in the negative portion of it. So as x goes to infinity, y is doing nothing. So the only type of end behavior we have is as x goes to infinity, our y is going to infinity. So we write that like this. So we say that our end behavior, the limit as x goes to infinity of our function, our y values are going to positive infinity. And we don't have any x values going to negative infinity, so we don't have to write it. Next, we want to look at where our function is continuous. And as we are analyzing and looking at our function, we see that our function is continuous at this point, but it's not continuous everywhere because it doesn't exist over here. So the way we write that is that we are going to write that our function is indeed continuous, but it's continuous on a specific interval. It's continuous on the interval 0 included to infinity. Now the last thing we want to do is look at the intervals of increase and decrease. And we see that our function is indeed increasing everywhere on our domain values. So we write that in the same way that we wrote our domain. So we would write that our function is increasing on the intervals from 0 to infinity. So as x is from 0 and as x goes to infinity, our function is always increasing.